I am on air. We're live, guys.
Okay, so we can start. Our last talk for today is by Vishal Aggarwal from Leeds. And unfortunately, the title is so long I cannot remember, but I'm sure Vishal will tell you.
Yep, so today I will be talking about a construction of uncountably many maximal closed subgroups of some n by redux of the Henson digraphs. So I'll start by giving definitions of the term redux. I'll go review the definition of closed and what the topology is that I'm discussing. I'll then state the main theorem of the paper that I'm discussing today, and then most of the time will be used to show how that theorem gives us uncountably many maximal closed subgroups. I should say this is joint work with Michael Kompatscher. He's a PhD student in Vienna of Michael Pinsker. So let's just start with a definition of a reduct. This is all in first order logic, and whenever I discuss structures, I only discuss countable structures. For this reason, you can just assume the domain of all our structures is n, the integers, and the consequence of that is that automorphism groups will be subgroups of the symmetric group of n. Okay, so definition. So we have two countable structures, A and B, and they have the same domain. We say that A is a reduct of B. The intuition of the definition is that A has less information than B does. The formal definition is that all the zero definable relations of A are already zero definable in B.
Oh. You mean definable without parameter?
Yes. So that's what I mean by zero definable or empty set definable. Yep. Okay. So a question that is often asked in this with this term is usually a structure is given, and you're interested in what are its reducts. But there is a caveat which is involved because you can imagine there's a lot of redundancy involved. You can add in lots of the definable relations as symbols. So there's a equivalence. So if two structures are reducts of each other, we consider them to be the same. So there's a caveat. If, let's say, A and A prime So then the question would be, given a structure, what are its reducts up to this equivalence? So I'll just give a couple of examples of structures for which this question has been answered. So one example are the rationals with a linear order. And something like I should have said is that the reducts of a structure form a lattice. So at the bottom, we have the structure that has the most information. As you move up the lattice, you lose information. Always at the top, you'll have the structure which has the least possible amount of information. That's just equality. Now, what are the reducts of the rationals? Well, on one direction, you can have what is known as the betweenness relation. The betweenness relation is a three-area relation which says x, y, and z are related if y is in between x and z. That's what the betweenness relation says. We have then a cyclic relation. This is also a three-array relation. And in this, the picture we have is imagine taking the rationals, then wrapping it around into a circle. So here, let's say there's 0. Here is infinity, if you wish. And then what you do is you take any 3 points, A, B, C, and these 3 points are in the relation if when you join up A, B, C in the order, they go in a clockwise direction. So for example, if I gave you, say 0, 10, minus 3, if you drew 0, if you draw 10, draw minus 3, join them up, go in a clockwise relation, hence it holds. Then over here, we have what is known as the separation relation. This is a 4-array relation. What does it say? So you have 4 points, A, B, C, and D. I might need to simplify this diagram a bit. So separation relation, A, B, C, and D. And 4 points are related by this relation if C and D separate A and B. And, well, the result is that these are all the reducts of the rationals up to this equivalence. And this follows from a theorem of Peter Cameron from the 70s, in which he classified the highly homogeneous permutation groups. All right. So that's an example of redux. Now I'll discuss the symmetric group of n. Just recall what the topology is that I'm discussing.
So are there always finitely many reducts, or are there more complicated structures?
So I mean, like a silly example is if you just have have a constant symbol for every element of your structure, then you can get lots and lots of redux.
Yeah, but if you have a finite signature.
Right. Okay. Well, so that's a very good question. There is a conjecture in this area. I was going to mention it, but might as well mention it now. It's a conjecture of Simon Thomas, which he stated in his paper in the 90s, which says that if you have a countable structure in a finite relational language, then it has finitely many redux. I'll mention what the word homogeneous means soon enough. So I'll just write it down. All that's a conjecture, and this is one of the motivations of studying the topic of redux. So the symmetric group of n, it's a well-known fact that this forms a topological group, in fact a Polish group. The group operation is just composition of functions. The topology is known as the pointwise convergence topology. For me, what matters is what does it mean to say a subset is closed. And the way I define this is I'll define a closure operation, and then a subset is closed if it's equal to its own closure. So let's take F to be a subset group. and G to be an element. So what does it mean to say G is in the closure of F? Well, the intuition is just that G can be well approximated by functions in F. More precisely, the definition is just that for any finite subset of the integers, we can find a function in F which does exactly the same thing that G does on that finite subset. So if for all finite A sub n, there exists a function in F which agrees with G on A. All right, and so this is the definition of a closure operation. A subset is closed if it's equal to its own closure, and you can check that this gives you the same topology known as the pointwise convergence. So now, what is the relationship between closed subgroups of sim n and this notion of redux? Well, we have this very important fact. So if you take any subgroup of the symmetric group, then G is closed if and only if you can find a structure such that G is its automorphism group. So in one direction, both directions are fairly straightforward. One of them is just an exercise in sort of unraveling definitions, and you just see that it all works. So if you have an automorphism group, you want to check it's closed. Well, this is all to say that G can be imitated by F, or G is well approximated by an automorphism group, is the same thing as saying that G preserves all the relations that are definable in your structure. Hence, it's in the automorphism group. In the other direction, given a closed group, what is the structure that you define? You just define the structure to be all the relations, so all the orbits of this group will be the relations of your structure. So for every orbit, you just add a new relation symbol, which will be interpreted as that orbit.
So what's the domain of that structure?
The integers. The set of n, just n.
N.
Yeah. Yep. So via this fact, you have a nice correspondence between sort of model theoretic language and group theoretic language. And there's a second important fact, which has a little caveat. So if we know that M is L0 categorical, then we have a correspondence between the following two collections. The first collection will be the reduct of M. And the other collection will be closed supergroups of the automorphism group of M. So G lies in between autem and the symmetric group. Out-of-zero categorical just means that M, if you have any other structure which satisfies the same theory as M does, then it's isomorphic to M. Okay, so maybe to highlight this correspondence, I'll describe sort of the group side of what goes on over here. I mean, I could just say take the automorphism groups, but maybe I should say a word or two. So over here, we just take the automorphism group of the rationals. To get over here, we just need to add a function which flips the direction of the line. So, well, maybe I should write something now. So at the bottom, I have all rationals. So over here, what we need to do is just find a function going from Q to Q, which satisfies the following. X is less than y, if and only if f of y is less than f of x. As an example of such a function, you just multiply by -1. And so you can just add this function to this group and then close under group operations and the topology. And that will give you so these angled brackets just mean smallest closed group containing these elements. On this side, what kind of function do we need to add? Well, the function you need to add, if you take your rationals, take pi, well, what you can do is you can find a function which sort of maps this over here, which swaps around these two pieces, but doesn't change the order in the two pieces. So there, I mean, both of these are countable dense linear orders, so there is a function which witnesses this. Let's call it, say, G. And then over here, all we have to do is you throw in both of the functions together, and at the top is just the symmetric group. Okay. Are there any questions so far? Nope. All right. So what I've been doing is the main theorem of the work that I've been doing in the past year is that I determined the reducts of the Henson digraphs. So the Henson digraphs are the things I'll describe next. So for me, a digraph will be, digraph is just short for directed graph. You have a set of vertices, and the edges have a direction. So we have, these are the three possibilities given any pair of vertices. I do not allow edges going in both directions. So those are not allowed. So there's some papers where digraph does include this, but for us, at most one edge between any two vertices. So what are the Henson digraphs? So in the 70s, if I remember correctly, Henson found this construction of uncountably many homogeneous digraphs. So at the time, there weren't that many examples known of homogeneous structures, so this was quite an impressive result. And I'll just describe the construction now. So we let T be any set of finite tournaments. A tournament is just a digraph which does not contain any non-edges. Another way of saying that is between any two vertices there is an edge. You should think of this curly T as being a set of forbidden tournaments. So I start off with this curly T, the structure I end up with, none of these tournaments will be embeddable in the structure. And then at 4T will be the set of finite digraphs which do not embed any of these finite tournaments. This is D a finite digraph. Such that for all finite tournaments in T is not embeddable in D. So just as I go, like a degenerate cases, for example, if T was just the empty set, can anyone say what 4T would be? Yep, so 4T would be all finite digraphs. The second degenerate case is if I have the one element tournament in there, then it'll just be empty. And then the last degenerate case is if it contains the two element tournament.
No edges.
Only contains singleton tournament.
So we have a few different options.
There's M vertices and none of them.
Yep. So these are all the edgeless digraphs. So these three examples I exclude because they exhibit behaviors which are not of interest. So what do we do once we have this collection of finite digraphs? Well, there's a theory of homogeneous structures. Developed by Freyse, and it turns out that this class 4T formed what is known as an amalgamation class. I'm not going to list the conditions, they're not really that interesting if it's the first time you've seen them, but it's all very easy to check that it all holds. So then, finally, we get to our digraphs. So dt I will define to be a countable digraph which satisfies the following properties. So A, it's a countable digraph. Second thing is that a finite digraph is embeddable in dt if and only if it came from 4T. So D and the last condition is of being homogeneous.
So this dt, it embeds everything in 4T, or should it embed nothing in 4T?
No, it does embed everything in 4T, but it does not embed anything in T.
Oh, right, okay.
Yep. So like a double I don't know, some kind of negatives. So the last condition is that it's homogeneous. And maybe I should say why is this a nice condition to have? Well, I've rubbed it off now, but we had the conjecture before, which is that all homogeneous structures have finitely many reducts. So this, well, something worth looking at then. what is the definition of homogeneous? Very, very roughly speaking, it says that the structure looks the same no matter where you are inside it. That's a very rough intuition. Precisely, it means that any partial isomorphism from finite subsets can be extended to an automorphism. So every G So these are the three conditions. The fact that such a DT exists follows from the background phrase theory. Another important fact is that these three conditions actually determine DT uniquely up to isomorphism. If you've never seen homogeneous before, maybe a quick couple of examples to give you a bit of intuition. So actually, non-examples. So the first non-example will be just n with a linear order. So can anyone tell me why n with a linear order will not be homogeneous? So the least element? Yep. And so, and another element that is not least. Yep. So for example, you can map, say, 0 to 1. That is a partial isomorphism of linear orders, but you can't extend it. Then if you had z with less than, well, now you can map any element to any other one. But you can increase the spacing. So for example, 0, 1 to 0, 2 is a partial isomorphism, but there's no way to extend it. And then you have q less than. Now this is homogeneous, and it's a very, very straightforward exercise. All right.
But what if you take, for example, rationals with reflexivity, and for example, radograph?
Yep, so the radograph is a homogeneous.
But the disjoint union of these two structures.
Disjoint union.
They are not the same everywhere, but according to the definition.
Oh yeah, so that's why it's a rough
Because
intuition.
Reflexivity. Because each automorphism, each finite partial automorphism must map reflexive point to reflexive point, and irreflexive to irreflexive. This disjoint union is, these two components are completely different.
Yep.
But this is homogeneous.
Yeah, so I mean,
Okay, doesn't
so
matter. But
yep. So when I said the intuition is it looks the same everywhere, there's a little caveat, which is if you look different finitely, then your opinion of the structure might be different too. So if I'm red and I'm blue, then maybe red people have a different view of the structure from blue people. Okay. Okay. So now, what is the statement of the main theorem? So I need just first a few definitions before I can state the main theorem. So first, I will let this minus or this dash denote a function from dt to dt. Which satisfies the following property. It's a complete analog to multiplication by -1 for rationals. So this will be a function which changes the direction of all the edges. So for all xy, there's an edge from x to y, if and only if there is an edge in the images. Something I should say is this function might not exist for all choices for curly t. So for some choices for curly t, you will be able to find such a function. For some others, you won't be able to. So I mean, in words, this is just a function which changes the direction of all the edges. Similar to how with the rationals, multiplying by -1 changes the order.
Can you give an example for which you cannot find such
Essentially, all you need to do is check if you apply this function to the tournaments, you have to make sure that the resulting tournament is also forbidden. That's essentially all you have to do. Then I'll define something called the switching function, which is, it's the same idea, but you only flip those edges adjacent to one particular vertex. So you pick a vertex and switch the direction to those. To write down the condition is actually a bit, if I write down the definition, you get more confused. So pick a point, it has a whole bunch of outgoing edges, incoming edges, non-edges, and just flip the direction of all of these and keep everything else the same. Then we have the random graph, which I'll denote as gamma. If you haven't seen the random graph before, it can be defined as follows. It's the unique countable graph which satisfies the following extension property. So for all finite u v gamma, I should say that disjoint, you can find an x which is joined to everything in U and not joined to anything in V. You can find an x. And then we have similar functions, but with respect to gamma. And then you have switch gamma. So this will be a function which swaps edges with non-edges. And this will be a function which swaps non-edges and edges adjacent to a particular vertex. Right. So now I have all the definitions I need to state the main theorem. So gamma is just a undirected graph. Yep, I should have said that. Yes. Okay, so then solve this. Let dt be as constructed. So these are the things which are known as Henson digraphs. I should have said that. Then its lattice or redux is a sublattice of what I'm about to draw. So at the bottom, I'll describe it in terms of the automotion group. And then one option is we could have added the dash. The other option is that we could have added the switch. Then directly above this, you can add both. Above this, you have gamma, then you have switch gamma, then you have both, then you have this metric group. That's not a very nicely drawn diagram. And I should stress, so there are a few little extra details which basically say, how do you know when which case is which? They're all fairly easy things you can check. All right. So now you can use this result to construct uncountably many maximal subgroups of sub n. This was a question which was asked by Dougal and McPherson. He's asked various questions about the symmetric group of n and maximal closed subgroups in particular. And one of the things he was interested in is, can you find uncountably many maximal closed? What do I mean by maximal closed? Well, what I mean, so G is maximal closed if G is itself closed and there's nothing in between, which is a closed subgroup. So we can use this to find uncountably many, and the main idea is, well, if we're able to find uncountably many Henson digraphs, then we should be able to find uncountably many maximal closed subgroups. So how can you construct uncountably many Henson digraphs? Just a few observations that need to be made.
What is a Henson digraph?
Oh, so a Henson digraph is a digraph is something of the form D curly T. Yep. I forgot to say that earlier. So I'll say a digraph is a Henson digraph if it's equal to D curly T for some curly T, and excluding those three degenerate cases. Okay. So how can you construct uncountably many of these? So the first thing to notice is that we may as well assume that T is an anti-chain. And that's because, well, let's say that we had T1 embeddable in T2, and these were both in curly T. Well, then T2 is redundant, because once you've forbidden T1, then you've automatically forbidden T2. So you can just take all the minimal elements of curly T, so you may as well assume T is an anti-chain. The second observation is that if you have two different curly T's which are not equal, and they're both anti-chains, then the resulting Henson digraph will be non-isomorphic. Again, it's quite easy to see because, well, they forbid different tournaments. So how do you get uncountably many? Well, all you have to do is find an infinite anti-chain. So once you have an infinite anti-chain, you can just take any subset of that to give you a different Henson digraph. Now, how can you find an infinite anti-chain? So this is a clever construction by Henson. The idea, as Cherlin, so I had a conversation with Cherlin, and he just said, oh, the idea is just to encode paths of length n to tournaments. Oh, it's at the top. Oh. I mean, it looks like there's extra space. It's a bit deceiving. Oh, okay. Okay. Right, so how do you get an infinite anti-chain? So I'll define the tournaments, which I'll label as IN. How do I define IN? Well, I start with a linear order. On n elements. So if it's a linear order, everything is pointing up. But then I modify some of the arrows. So then I'll change consecutive vertices, so everything which is consecutive goes down. And going from n to 1 is also going down. So every arrow I haven't drawn is still going up. Now, how do we show, well, then the claim is that IN, for n greater than or equal to 6, forms an anti-chain. How do we show this claim? So what you need to do is you need to count the number of different 3 cycles that you can embed into this. A 3 cycle is just a tournament on 3 vertices going in a cycle. So there are 2 different options. Well, option 1 is I go up twice and then down, or you go up once and then down twice. So if you're going up twice and then down, well, the only edge going down at least 2 is this one. Every other edge going down goes down exactly 1. So all the ones of this kind must contain a 1 and an n. What are all the other options? Well, you can have 3, you can have 4, 5, all the way up to n minus 2. So these are the different 3 cycles. Then how about this kind? Well, you have 2 going down. The only way you can get 2 down is if they're 2 consecutive downward edges. So you can have 1, 2, 3, 2, 3, 4, all the way up to n minus 2, n minus 1, n. Now, why is this of any use? Well, the reason is we can now define a graph relation based on this tournament, which is we connect 2 vertices I and j if there are at least 3 cycles containing I and j. So, for example, would 1 be connected to 2 via this green relation? So which of these 3, can you all read? Is this too small? Yep. I mean, yep, okay. So which of these 3 cycles contain both the numbers 1 and 2? Just 1, 2, 3. So that means we don't connect 1 and 2 because we only found 1. How about 1 and 3?
They're right there.
Yep, they're right there. Yep, so we do connect them. And if you just go through them all, you'll connect 1 and 3, 3 and 4, 4 and 5, all the way up to n minus 2, n minus 2 and n. And the reason we need n greater than or equal to 6 is to guarantee that we can connect this one up. So now what have we done? We have a cycle of length n minus 2. If you were able to embed, say, n into ik, then it would imply that these cycles would have to be embedded into each other. And clearly, a cycle can't be embedded into a different size cycle. So now we have an infinite antichain. This gives us infinitely many non-isomorphic Henson digraphs. But the issue is we need to check that the automorphism groups are maximal or not. And well, it turns out that they're not quite maximal, because just by forbidding these, if you notice this tournament is, if you change the direction of all these of all the edges in in, you end up with in again. So we just think through the definition, which means, for example, this group will be inside it. A small exercise, you can show that gamma will also appear. So we don't have maximal closed subgroups. Well, how do we ensure we have maximal closed subgroups? You can just forbid a few extra tournaments to essentially just kill off those 2 options. And that's roughly the idea. I think I'm out of time, so I'll stop there.
Do we have some questions?
So the conjecture you mentioned at the start, right? The assumption that it was countable, is there a counterexample otherwise?
I'm actually not sure. I somehow count as the countable homogeneous structures which have been studied the most. I don't actually know the reasons why. John, do you know? What do you know why?
Uncountable homogeneous structures are very wide.
Okay.
I mean, with 2 to the L of 0 dense linear orders without any. So 2 to the L of 1 dense linear orders without endpoints which are homogeneous.
Okay.
Because that doesn't mean that any individual one might not satisfy this.
Sure. Yep.
So I was going to, so for the digraph without forbidding things, which
Yep.
you also looked at.
Yep.
You had a couple of extra reducts.
Yes.
So you presumably use those in all these Henson things. did you?
Right. Yep. So one of the degenerate cases was when you forbid node limits. Then you get what's known as the generic digraph. So that was actually something I worked on before this. It turns out there are two extra little reducts. You end up over here. But because you forbid tournaments, it turns out that these just disappear.